so-called training data. And so once you start to address these problems in areas where the training data may not exist or it's going to be sparse, that's where some of the self-learning models, or as we are calling them, geospatial foundation models, starts to play a role. So here it's really just you train one of these massive amount of models, right, with millions or billions of nodes, and then you are training it such that it starts to learn some of the connections or interdependencies between various parameters. So just to give you an idea, right? So as I was mentioning, we used to have some of these systems, where you had, for example, a data set, right? You had a model, right? And you had a specific task. And with our approach, right, of this foundation model, it's really that you take now huge amount of this unlabeled data, you train the model, and then you are going to have multiple of these so-called downstream tasks. And once you have this downstream task, then you can fine-tune it towards a very specific area. And our interest is mainly about, for example, detection of wildfire. Can we really try to classify some of the trees? How can we quantify, for example, the canopy height or some of the above ground biomass? So in general, the way that we are approaching the problem, it's very close to what you have seen probably in the ChatGPT, where people are blocking out, for example, a single word, right? And then you start to learn from that sentence what will be the contextual informations in order to recreate that particular, let's say, word. In the geospatial domain, right, of the imagery, we are blocking out various parts. So what you're going to see here, you take, for example, an image, you block on purpose out various parts of it, and then you're forcing the system to learn about reconstructing that particular imagery that has been blocked. And so you train this model until you reach the performance that was desired from the beginning. Uh, so in general, you can now see, how the system is working. Really, you could quantify, through various ways about reconstructing, for example, the missing data. You could use, for example, different parameters that, like mean absolute error or RMSEs in order to create some of this imagery. Now, once we have some of these models trained, we essentially are able to fine tune it towards various tasks, right? So, and just for the sake of time, the way that we are approaching the problem is that we are taking measurements that it's coming, let's say, from this LiDAR that it's on the top of International Space Station. It's called JEDI. It's operated by NASA. And what you can do is you get very sparse measurements. Those are going to be those red dots that you're going to see on the left side, so this laser, it's like just pretty much like a laser pointer, it's just sending down a small pulse, it's getting back the data. And the idea is then to take some of these very sparse measurements and reconstruct what is happening in between, let's say, these points. And you use various models. We use satellite data. We're teaching some of these models to now learn what is in those areas where we don't have ground measurements. And what we can do at the end of the day, it's going to be creation of these so-called continuous maps. You see here, for example, how it looks for Africa, where we are able to now reconstruct from very sparse measurements some of these larger scale models that are covering the whole globe. And obviously here, the big question is, okay, we created these models, the performance of it can be quantified, let's say, based per ecoregion, but we want to make this model as accurate as possible on the local scale. And that's the point where we essentially trying to understand nowadays, for example, what are going to be some of the noise that is carried in this type of measurements, and then essentially come up with various ways in which we could overcome some of this noise that is carried by the remote sensing observations. And so, for example, if you would look just to the very simple parameters, that could be the EVI that it's plotted here, we could essentially start to see, for example, the variations that we have across the globe. And we can take, for example, an area and quantify, for example, the overall carbon that is sequestered in that particular region. Using only some of the satellite measurements, what you're going to observe that there is some type of fluctuations in the signal, meaning that there is around 3 to 4% variations in the overall estimate that you have year to year that is coming from some of these measurements. So the way that we try to approach this problem, it was really about going out and specifically trying to use some of these flux tower measurements, addressing not necessarily the year-to-year predictions of, let's say, the above ground biomass or the carbon that is stored in the vegetations, but rather than we are trying to solve the problems of accumulations of the carbon within the vegetation. And this is an important aspect. So you really want to have certain type of, let's say, background that is going to be your overall pool. And then you want to quantify year to year what is going to be the accumulated, let's say, carbon that, for example, a private company or somebody who is investing in some of these carbon stocks would be willing to go, right, and use to offset some of their greenhouse gas background. And this is something that is called net zero. So essentially, you just buy up some of these carbons as these carbon pools are increasing, then that increase in the carbon pool, if you maintain those areas or those, let's say, carbon pools, then you could use it again. So what we started to create was potentially some of these data sets that we essentially taking some of these values of GPP, and then we are looking across multiple years just to try to understand exactly how we can relate the growth the measurement that is coming from some of these flux tower measurements directly to the increase in the carbon pool that we are getting from many of these measurements that we could create out of these AI tools. And essentially, we get to the point where we have some training data, but obviously with any of these AI models, right? 50 sites or 200 sites, it's obviously little. The desire is going to be towards thousands or tens of thousands of these towers, so that we could now get a better understanding about the dynamics of the growth that is happening in a particular model. And so we combine various ways for this model. So we are using just purely data-driven models that it's going to be just some type of correlations. We can have some of these physics-based models, right? So we have some of the three growth models that I'm going to present in a second, or we try to combine both of them. Now, obviously, this is one data source that it allows us to now calibrate models on a very local scales, and we can pinpoint these models and then force the AI to learn on this local scale what is happening with, let's say, the value of the carbon and then an increase or the growth rate in a particular relationship. The additional data sets that we could, for example, use, and we were looking a little bit into this one, it's really some of this report that, for example, Vera, through some of their registry, it's putting out. So these are vetted by the scientific community, where it has been agreed that they are going to be the carbon, let's say, background or the overall carbon that is sequestered for a particular project. You have also projections of the growth of that particular area based on different physics-based models. And sometimes it's just a simple addition that is happening there. But these are another anchor points that now it allows us to figure out if the model that is created by, let's say, these foundation models, it's comparing with what local experts going to agree on the ground. And so in this whole process, we have also tinkered quite a bit using, for example, some tree growth models. The one example is shown here in the lower one. It's called 3PG. It essentially allows you now to take, for example, climate data and integrate it into a model in which you're going to have some information about the soil. And then in particular case, now you're going to have something that it's growing year to year, that is going to be the third validations, right? That we are comparing with what, for example, Vera is doing, and then we are trying to compare it also in regard to what we are taking from some of the flux tower measurements. So overall, it's a lot of number crunching, right? That it's happening in the background, right? And I think that here the main argument, right, that we try to make is that really, once you, for example, create these transitions from, let's say, local measurements to the regional, right, it's going to be a need, right, to go back again, and revalidate or make sure that, areas that has not been covered by measurements are going to have as less uncertainty as possible, and they are as accurate as you can get. And obviously, there are different tools that you can use in this whole area. And the flux towers, we are seeing it as a valuable measurement that it's happening on the ground, right? And it's providing us long time series across a certain area, across a certain time period, where we could understand the dynamical behavior of some of these systems. And obviously, this is going to be, for example, the first step that we can use in order to quantify exactly what's happening there and how it is changing, right? And obviously, I think that, the final message that probably you have to take away is that, there are all these measurements, but at the end of the day, some of these AI tools and methodologies are going to be extremely important, because at the end of the day, you need some ways in which automatically you are going to be able to produce some of these results that now could be used, for example, to enable a carbon trading market, or just to better understand, for example, what is the carbon exchange between the atmosphere and the land cover. Thank you so much.
So different plant functional types, or you could have, 30 different species. And much of the project finances or the whole project viability is often dependent on the first 10 or 15 years of growth, which is very related to the different species that you plant. So you refer to fine tuning for specific projects, and I was curious how you see this evolving in the future, where you can take a foundation model and integrate knowledge of individual species and their different growth patterns or niches that they occupy in a system to get to those, what we ultimately need for these projects is hyper-localized projections.
So sorry, I didn't hear the first part of the question, as I think that the room was muted, but just to give you the perspective, from our side, one of the trick, that it's happening with this foundation model, it's really that as you mask out, randomly, let's say various parts of the image, the model starts to learn the long-term correlations between various parts. So if you take, for example, a couple 100 kilometers and you have, let's say, the same type of species that it's usually happening, on a certain regions, if you learn something on a particular area, then you could very easily translate it, to areas that are sharing the same type of characteristics. And so this type of longer range correlations, it's really playing an absolute role here. Uh, in the past, people did use, for example, convolutional neural network. There, you're going to capture the local, let's say, contextual informations. But the long-term relationship, right, between various parts of the imagery, it's always lost. So here, one of the advantage of some of this a foundation model is the possibility, right, to learn longer term correlations. And so if you have enough of these data points, it's going to be more than one data point, right? But certainly you don't need to have for every single location a data point. If you have representative data points, then you could easily translate, some of this knowledge that you build up on the local scale, to other areas that are potentially, have no direct measurement.
Fascinating. Thank you.
First that.
One question that I have is, how are you in your modeling or AI ML approaches dealing with spikes? And have you dealt with that? And can you share what the outcome of that one is? So specifically, we're looking at greenhouse gases that have diurnal patterns and that have spiky patterns. And traditionally what we see is that when we do gap filling of that, spikes are basically ignored in all the existing models, and they are just basically plastered in, which means that we're losing a large amount of really relevant data.
I'm not sure if the question was answered to me, but so our advantage is that, you know, we are really looking into, let's say, predictions of once or twice per year. So what's happening is that, you know, even if we have, let's say, a very dense time series data, right, we are trying to collapse that one as much as possible, right, across, let's say, a representative value across the growing season. And so in that particular case, if you take any of these, let's say, statistical measures, right, the mean or the median values, you are going to wash out pretty much all of the so-called high values.
We have another question there, but okay,
Let me just clarify that. So what you're basically saying is that you're basically averaging for the entire season.
That's correct. So the challenge that we face with some of this remote sensing imagery is that you're always cloud contaminating most of the images, right? So what you need to do in order to create, let's say, just a above ground biomass map, you need to create so-called this cloud-free imagery. Sometimes, you know, depending on where you are on the globe, you know, it takes, let's say, 1 or 2 snapshots. Sometimes it takes across a whole season. You need to really look for a particular area to be able to create this cloud-free imagery. So that's the limitations, you know, it's kind of a time mismatch between what it's providing you, the satellite, versus what it's going to be, you know, the very dense, let's say, hourly data coming from the flux towers.
Hi, Levante. I also have a question for you about foundational models, and I've been thinking about them a little bit from the other way around and wondering, and maybe my thoughts are far-fetched because I don't understand it very well, but how could we build a foundational model from our field data? So not from the imagery, but to kind of use the richness of in situ measurements and build the foundational models, use those to fine tune with imagery to extrapolate.
So it's a different time scale, right? But I think that if you think about it, right, at least the way that we are approaching the problems, obviously the weather and the climate, it's playing an important role, you know, about how much of this carbon is going to get sequestered. And so we already have time series data that is coming into some of these models. Obviously, you know, it's going to be on an hourly basis or let's say on a daily basis. But it is informing some of these models. So I think that in the case of flux towers, it's going to be just to, you know, integrate properly, you know, some of this data. And where we are looking for is that, you know, how can we, for example, get some of this data as complete as possible, right? So I'm not an expert in flux towers measurements. So reconstructing of the missing data and all these things are, you know, it's like very difficult to grasp with my knowledge, you know, of the field. But obviously, if we would have, you know, this time series data, they are going to be extremely valuable, right? That we could integrate into the model.
Thank you, Levante.
Sure.
Hey, to Troy, a great talk. So one first question is how to scale up from the needle to shoot, because within the shoot there are lots of multiple scattering. So I'm curious how you consider that multiple scattering within the shoot into the landscape scale. That is the first question. And the second question is, there's a lot, very strong seasonal variations of solar zenith angle in high north. So how did you consider that angular effect in your GPP versus SIF?
Yeah, I think your first question is kind of one of the grand challenges in remote sensing at large in that like radiative transfer modeling is really kind of the best we can do to like scale up how these photons are bouncing around from individual needles up to shoots, up to trees. We've started to sort of explore some of that at the site scale using like high resolution LiDAR data, but even then, you know, you make a lot of assumptions. I think given that we're just sort of like averaging a lot of different needles of different trees kind of across the landscape, we're kind of just doing the best we can to characterize uncertainty. And then your second question was about, oh, yeah. Yes, this is also a big challenge, especially for coniferous trees, which, you know, under given times of day, they might be completely shaded or completely sunlit. I mean, the best like answer I can give you is that given that we're looking at many different angles throughout the day in these ecosystems, that sort of just averaging them out is the best we can do to sort of just hope that this is the canopy level average. We've done some more like, you can start to do like some more like sophisticated analyses where you're like actually looking at like phase angle, which is the difference between viewing and solar geometries, to see sort of where signals begin to drop off with certain phase angles. And under those scenarios, we tend to sort of just drop out data where it's under really high phase angles. So where that difference between the solar angle and the viewing angle is really high. Francis Ulip over here, PhD student in the lab, is laughing because he's spent the last 2 years working on phase angle corrections for some of our data. But you could find him during the break also to talk more about it.
And while you're at it, we have a question for you in the chat. So what should we consider when using PAM data for analyzing with canopy scale measurements?
Yeah, so I mean, with PAM data, it's tricky because you can only put enough sensor heads on, you know, we have 4 sensor heads on 4 different sort of needle clusters in the canopy. Again, it's sort of my same answer as the last one, which is just that you sort of just hope that this is representative of what's happening at like the canopy level scale. And we do like target our instrument right at where these MoniPAM measurements are being made, and then compare those spectral measurements across all the other trees within the field of view and find some kind of similar patterns. But yeah, thank you.
And I think there's another question, like, what do you think about the role of water in the phase of changing from PQ to NPQ?
I would say it depends a lot on the ecosystem. I mean, we can think of NPQ as sort of an integrated measurement of a plant stress response. So it could be due to anything from vapor pressure deficit to air temperature to xylem function to water availability. Water availability is, of course, one of the main drivers of plant stress. So it's a component, but it's difficult to say specifically that a stress might be due to X, Y, or Z.
Okay, let's take the next 2 questions before going to the breakout, okay?
Yeah, I have one question for the Hao-Shen. Nice talk. So actually, I really interesting to see how, you know, the considering the flux footprint, it really improved the, you know, the scaling problem. But our assumption to do it is the remote sensing is also really kind of pretty perfect, you know, the grid size. But actually the remote sensing itself also footprint level, and they have some uncertainty within the grids, right? So do you have any kind of, you know, the activity considering the footprint of the remote sensing in your, you know, the representativeness of, you know, the fluxes?
That's a great question. I don't have an answer. I think maybe you have. I think that's why we need to talk to each other. So realize the assumption and also limitation for both our data set. We haven't mentioned about temporal mismatch. It's also a big issue combining remote sensing with flux data yet. So I think that's a lot of work to need to be done. I don't have an answer for you, but I think there's something recognize the data set we're dealing with and what is the assumption behind that. I think it's important first step, and we can talk. Yeah. Thank you for the question.
So it was touched on a second ago about water in your work, Troy. But I guess my question was, I saw one of your sites was at Niwot Ridge, and I know they have some sap flow measurements there. And I'm just curious, have you looked into that relationship at all with SIF in particular? Because I know it's a question as we start.
Yeah, that's a great question. And we have. There was a paper in 2021, also led by Zoe Parat, who's led a lot of the work I presented today, where we looked at the sort of onset of sap flow in the spring, compared that with GPP and with SIF measurements. And the cool thing is we sort of see these sort of wiggles in the spring where SIF might be increasing or decreasing, and it seems to be in coordination with sap flow as well, which gives us, I think, a little more confidence in at least the sort of coordination between the light and the carbon reactions of photosynthesis. But we also have a bunch of dendrometers at a lot of these sites, and we begin to look at like daily changes in tree growth as well to sort of give us an idea of water uptake. And I think that's kind of something we're pursuing a lot more and more.
Awesome. Thanks.
All right, thank you, everyone. I think we're gonna divide again for a breakout session now. We have about 25 minutes before lunch. Okay, everyone, let's start with section 3. Hope you had a nice lunch. So our next speakers actually, Jacob Nelson and Samuel Upton from Max Planck Institute for Biogeochemistry. They are here to present the reconcile atmospheric carbon and water fluxes, integrated top-down and bottom-up approaches with FluxCom-X and X-Base. Jake, you're ready to go?
Yep.
All right, all yours.
Great, thanks. Yeah, I'll present a bit what's going on with FluxCom and some of the new products very briefly, and then I'll pass over to Sam, who will show much more interesting and exciting up-and-coming stuff. So first, I'll start with a bit of context and some history. So Dennis, feel free to correct me in the chat if I get anything wrong. But fluxes everywhere all the time. Concept has kind of been around since the beginning of FluxNet, is my understanding. And as soon as people started aggregating data sets over regions, they started training models and producing maps of fluxes based on eddy covariance data. And as the networks got bigger, so did the maps, I guess. And we ended up with global fluxes of carbon, water, and energy. And the question really became, okay, how do we understand this upscaling? We don't have a lot of global benchmarking, so let's do an ensemble, a comparison products, looking at different machine learning methods, different media forcing, different remote sensing setups. We summarized that kind of in 2020, showing our key findings from all the past work. And then we said, all right, let's rebuild the whole thing from the ground up. So it's not an esoteric collection of MATLAB scripts, but instead a framework
Let me see if we can reconnect with him. Yeah.
Back.
All right, Jake, we see you and hear you.
Yes, sorry, my laptop had a complete and utter meltdown. Hard restart.
No worries. Good.
Was boring history anyways. So we have the new X-based products. And here we have kind of as a benchmark the old Fluxcom products. And what you see really initially on the left side, we have the new evapotranspiration from X-base, the new product. And you have a much higher spatial and temporal resolution. So we're at 0.05 degree and hourly. So that spatial resolution is mostly coming from the remote sensing data, temporal resolution coming from Medio, in this case, ERA 5. And this puts us much closer to the what's actually happening. So the fluxes are happening at an hourly scale. They're dynamic with immediate conditions. So this is, on the one hand, I think a much better representation of the fluxes. And it's also just a technological improvement. We're able to crunch a lot more data with this new Fluxcom X upscaling framework that we've built. These fluxes are now about 4 terabytes of data per flux. And so we're much more flexible in how we can ingest data, how we can use it within the model. But we're not just interested in kind of technical aspects. We're interested in the science, we're interested in understanding. So if we look at okay, we've updated our Fluxcom upscaling products. If we compare them to both the old Fluxcom, so in that case, this is RS and RS plus Medio. These are 2 versions of the old ensemble. One is remote sensing only, one is remote sensing plus Medio. And then we have kind of our benchmark, which is 2 sets of inversions, the OCO2 ensemble and Carboscope. And you see there's a big difference in this globally integrated NEE in petagrams carbon per year. And if we look at where the new products are coming in, it's about a 10 to 15 petagram difference between the old versions and the new versions. And the immediate question that would be asked is, okay, what changed? What caused such a big difference? Was it a new machine learning algorithm? Was it new remote sensing products? And really, the main key difference here between the old and new versions is that the old Fluxcom is based on Latwheel, so the 2007 version of the eddy covariance data, and now we're using the most recent FluxNet 2015 or later data, and so really that's just showing the improvement in the underlying eddy covariance data, and to drive that point home under our system, if we have a global change of 1 petagram carbon per year of integrated NEE, that's roughly equivalent to 7 grams per meter squared per year at the tower level. So this really kind of goes to show how far both the techniques, the community knowledge, the processing chains, everything that has improved over 10, 15 years, which is really quite the achievement, I would say. So we have these new X-based products. So Fluxcom X is the new framework that we're using to test things. And X-base is kind of the baseline products. We have NEE, GPP, evapotranspiration, as well as a new transpiration product based on the ET partitioning from the Flux towers. All of these are available as aggregated net CDFs from the Carbon portal, as well as the full high-resolution ZAR, where you can subset your area of interest and access these. And there's a link to that in the X-Base paper, which you can find online, or email me. I'll send it to you. Going forward, so it's a framework. We've updated the system. We have new products coming out soon. New remote sensing, ensembles of machine learning methods, energy balance closure, all of these things. We're constantly improving and adding to the data set. So new eddy covariance data, new remote sensing data, anything that is relevant that we can get our hands on. Our baseline has already shown quite a bit of improvement. And we're hoping with this system, we can further that improvement. And most importantly, we want this framework to facilitate the understanding, how does what we're seeing at the site level translate to regional and global processes. And with this, I will turn over to Sam to talk about the future.
Great. Thank you, Jake, and it's a pleasure to be here. So yeah, I'd like to talk about my work, which I would say is an extension of the Fluxcom modeling structure, the Fluxcom system, and in place as an extension of it, as I try to integrate bottom-up and top-down information into global flux modeling. Next. So the structure that we are working with is to take on the left side of this, which is the idea of Fluxcom using data-driven modeling to take eddy covariance observations and to create a global model for upscaling, to output flux densities and compare them in the objective function with eddy covariance observations. And what I think has been suggested and what we are really trying to approach is how you can then continue to enrich this information and improve the model by integrating additional information outside of the eddy covariance record. We are using atmospheric information, and the full schema of what we'd like to achieve is this, where we are transporting these fluxes and then doing our constraint against observations of atmospheric concentration. But for this study that is published that I'd like to share with you today, we wanted to put a test on whether atmospheric information could validly or productively enrich the information available to the model. Next. And so what we targeted for this first study is we targeted an ensemble of atmospheric inversions to be our atmospheric information in our constraint. We chose the atmospheric information, or excuse me, the atmospheric conversions because as that community has evolved and the atmospheric conversions have improved, irrespective of their fossil fuel priors and their transport methods, they are really converging on what seems to be a very, very realistic estimate of the land sink, which is also consistent with other independent data sources. Next. And so seems like a good idea. People have been suggesting it. Why hasn't this already been done? And one of the major issues is there's just quite some complexity connecting the dots between these data. First, obviously, is the scale. You have EC observations representing this small homogeneous footprint. Relatively speaking, is point data, and when you think about the land surface, informative just at that local level. Atmospheric conversions, on the other hand, they really are not reliable at the ecosystem level. They are really aggregates over regions where the estimation is stable. Next, there are of course the quantities and sort of the conceptual quantities are quite different. Eddy covariance NEE, which is a very, very isolated, pure representation of that biogenic flux. And it's in micromoles CO2 per meter squared per second, whereas the atmospheric conversions are seeing, multiple atmospheric stations are seeing a sort of a long-term state of the atmosphere, and they're exposed to the full composition of CO2, all of the sources of CO2 in the atmosphere, and then reintegrated regionally into petagrams carbon per month. Next. And of course, then in both products, there's quite some uncertainty. In eddy covariance, the NEE, noisy. In tropical regions, there's issues of bias from the technique itself. And of course, as we all know, the eddy covariance record is sparse, both in space and time, and that is exacerbated in the tropics, where collection is more difficult. And then atmospheric conversions, you're inheriting uncertainty from their transport and from their fossil fuel priors. Next. And so building this bridge is just took some work. Next. One of the big things we had to overcome in bridging this gap is the order of magnitude of the calculations and the bottleneck. One way to compare a region flux integrated over a month would be to run the model for every pixel in the region for all time steps. What this means that in a training loop, you are essentially doing forward runs of the land surface. And this is, simply speaking, computationally out of bounds. So we had to find a valid way to shortcut that computation. Next. And so what we hit on was using lasso regression, which is an extension of ordinary least squares, which tends to drive individual parameters to zero. So you tend to get a sparse solution to a linear problem. And what we did is we sort of made all the locations in the land surface to be potential parameters. And then we used lasso regression to find a stable linear solution between a small subset of pixels on the land surface, non-tower locations, and the regional integral of NEE for that region. Next. And what you're left with, we did randomization tests. It's a very data sciencey technique. I do not want to make any strong claims about the meaning of these regions and the meaning of these locations, but you do get a high quality estimate of the region from this very limited subset of pixels. So in Europe, it's somewhere in the order of 20, 25 locations. In randomized, we did a lot of testing to see how robust these were. The figure on the right is showing a heat map of where pixels were chosen out of random subset bootstrapping experiments to see whether these connections were durable. And so we can see that there is quite some relationship between hotspots and the linear relationship found. Next. And so what we end up with is this double structure. On the one hand, and unfortunately, it looks like the slide got a little, there should be a little neural network in that box in the center. So we have two objective function terms. In the first term, this is FluxCom. So we are taking eddy covariance observations, co-located remotely sensed variables. we are outputting an estimate of the tower level NEE, and we are comparing it to an observation. This is what we consider sort of the physical core of the model. This is where we are keeping the model grounded in the eddy covariance record, which we consider the sort of in this system the gold standard of information about the flux. And then to that we add a second objective function term, which is this atmospheric information. And so now for every region, we use the recap 2 regions. For every region, we take the pixels identified by that linear model, we pull the driver variables out of the global data cube, we run them through the neural network, we get an estimate of those pixels, we then apply the linear model, and we end up with an estimate of the region, which can then be compared against the atmospheric inversions and their estimates of those regions. And that creates our second term, and these both on every training loop update the weights of the model. Next. And before I get into results, I want to very strongly stress that these are not comparing to Jake's X-based results. This is a comparison with Fluxcom V1, the RS plus Medio. So you can see in the top left, I am showing something that's consistent with that negative 20 or so petagrams of carbon. But the top line result is that we saw quite some impact from the atmospheric information for every training run, so we could understand the impact of the atmospheric information. We ran an identical set of models, one with the atmospheric constraint and one without. One is just a eddy covariance based model. So the green in the figures is the eddy covariance model. The blue is the eddy covariance plus the atmospheric information. And then red, the inversion, the mean of the inversions. Yellow, which can be sometimes hard to see, I apologize, in this slide, is the Fluxcom RS, the Fluxcom V1. And then the black is the Global Carbon Project. That's the residual, the land residual. And what you can see is there's been quite some adjustment between these two with the atmospheric information away from the Fluxcom V1 and towards these other independent estimates of the land flux. But unfortunately, in the bottom term, what we have really not made a lot of progress is the natural interannual variability. So we're finding the mean, but not so much the. Nope. I apologize. I'm no longer seeing the slides.
Did we lost Jake again?
Uh-oh, I'm sorry.
No worries. Yeah, I think we lost Jake again. Sam, I think you had like a minute or so left.
Yeah, I think at this point I will wrap up. I think we're not going to get Jake back in a timely manner, and I apologize for the hiccups. But I will only say in conclusion, the last figure would have been that we find that correction that was evident in the global results, it is strongly evident it strongly adjusts the tropics where the eddy covariance record is under constraining the model, but you see very little change in the extratropics where there is a strong constraint. So we see what we would like, which is that the model is learning where the eddy covariance is sparse, but not adjusting much at all where the eddy covariance is well constrained. And with that, I'd like to thank you all and let the next speaker take over.
All right, thank you, Samuel and Jack.
And if we use, because this is a tower by the Dennis Baldocki, and in all his towers, there is NDVI sensor. When we use the field NDVI sensor to compute NIV n times par, then you can see there is some more scatters. But if we use NIV from the 3-meter CubeSat images, then you can see all the relationship is well converged. So actually that means that PlanetScope is even better than tower-installed NDVI sensor, because tower-based NDVI sensor has the fixed footprint that doesn't match with the Flux tower footprint. And then now we also developed, because there is now PlanetScope data set also, and also there is a long-term Landsat. So we generate the long-term, the 3-meter Landsat images by using the double GAN model. So we can, now it is well possible to reconstruct very historical Landsat data sets at the 3-meter. Then I think we can even do better jobs to use, for example, 1990s harbor forest. There is Flux tower data set, and we can use the 3-meter. And now the Sentinel, it has much better spectral bands that include the red edge. So it enables us to compute LAI at very fine resolution. So this year, my current postdoc, Liang Wan, he did a great job. So we corrected canopy structure, biochemistry, and soil background effects by using the Procel inversion and so on. And we tested this algorithm, LAI algorithm, in the NEON dataset, thanks. So we tested all the NEON datasets, and we found that it works well. So our proposal is to generate the 10-meter LAI map everywhere in the world. And then we can make the very fine resolution, the flux maps. So that is LAI. And also we have also published the 10-meter chorofill maps in RDC this year. So again, we use the Sentinel because Sentinel has a red edge band that is very, very useful to retrieve the chorofill. So because now we can produce the maps of the chorofill and also LAI at the 10 meters. So that is huge. In the past, it is not imaginable. If you think about what is LAI, it is 1 kilometer or even 500 meters. Well, now we can make 10-meter LAI and chorofill maps. And then we can, in the past, I developed a biophysical model that is called BESS. So in the past, we run BESS at the global scale with the forcing of the 0.05 degrees. It is around 5 kilometers. Now we can run BESS at the 10 meter. So the left figure is the result of the multiple flux towers in the South Korea. And you can see it is scattered, but in the right side is the site GPP and versus the 10 meter, the BESS simulation. You can see it is very well agreed because of I think it is the power of resolution. And because South Korea is very heterogeneous and it is very complex. So we need fine resolution maps. And then let me move to time. I think I'm a big fan of the geostationary satellite. And here the Paul Stoy will have the session tomorrow. Please attend it. It's a very impressive one, live. And this is a case of GK2A. It covers the Australian and Asian countries, the whole Earth disk. And because it captures every minute of the land surface, so here you can see in Southeast Asia, there are lots of clouds, but the key point is that cloud is moving. So there is high chance to see the land surface through the moving windows. So it radically increased the retrieval rate of the land surface information. But the problem, the one thing that you have to remember is that it captures diurnal variations. So solar zenith angle shows strong diurnal variations, and sensor view is only nadir for the equator, and the other region is off nadir. So that being said, you have to do BRDF corrections. Otherwise, angular effect is very, very strong. So my PhD student, Song Chan, made a paper last year. So here, first we started from the Korean forest. It is not that water stress. It is summer monsoons, enough rainfall. And so we just applied the NIRVP. So it is NIR reflectance multiplied NDVI times par. And we used NIRVP from the GK2A, the Korean geostationary satellite. And left figure is hourly, and the middle one is daily. And you can see it captures diurnal variations pretty well, and also daily. And the right figure is the diurnal variations in each month. So overall, it captures the diurnal variations of GBP. And as I mentioned briefly, it captures hourly, daily, weekly, monthly. But here, the blue color is top of atmosphere, so the TOA. And the orange color is surface reflectance. And the magenta color is normalized reflectance. Normalized means that it is with fixed solar view angle as like 30 degree, and the view angle as the nadir, for example, something like that. And by using normalized reflectance, then the slope is fairly consistent across hourly, daily, weekly, and monthly. That tells that. So it is very important to correct all the angular effects. Otherwise, angular effect could be even stronger than vegetation change. And now we try to generate the sub-daily SIF datasets by fusing the geostationary satellite, the GK2A, and OCO3. And we applied those machine learning models. So we retrieved blue, green, red, infrared reflectance, and shortwave radiation MVPD from the geostationary satellite. And we use SIF from the OCO3, and we built a model, and we predict a SIF using geosatellite. Here you can see the top left figure is the data that is OCO3 SIF. You can see there are lots of the gaps through the between swath is very, very large. But in case of GK2A NIRV, you can see there is no gap. And the bottom two figure is the data availability. The bottom left is modest BRDF data availability. And you can see in the Southeast Asia that there are lots of clouds. So data availability is pretty low. But if you see the GK2A BRDF data availability, that is the bottom right figure, even Southeast Asia, in such cloudy regions, still we can get very high quality BRDF parameter because lots of data from geostationary satellite. And so we built a model, and we generated hourly SIF maps in this whole, in this Earth disk. Overall, we found that morning showed higher SIF, and even SIF yield was higher in the morning than afternoon. So in the previous paper, I showed one example in Korean Peninsula that is not so much water stress. But here, we found that afternoon SIF yield was lower, and it is very, very strong in case of Australia, where water is limited. So we can see that we can detect the physiological signals of the SIF from this data set. And my former postdoc, Sing Lee, also used, in this case, he used the GOES data sets. He built the model. And in this case, that is GBP. Because GOES captures every hour, even 5 minutes. So that being said, we can see the diurnal symmetry of the GBP. So here, the left figure is the temperature anomaly. It is, I think it is 2020 when there's very severe heat wave happens in United States. And the left figure shows diurnal centroid change. So you can see overall the peak time of GPP is shifted into the morning. That was detected. And yeah, also that is very useful because in the past, in the modest period, we quantified the daily sum of GPP using just single snapshot and applied cosine function. But that assumes that diurnal symmetry of the flux, but that is not true. In stress ecosystems, there is diurnal asymmetry. And such thing can be now captured, and we can make more robust daily sum estimates from the geostationary satellite. And then finally, let's move to spectrum. So that is one example. That is Australia. And you can see there is I just chose one spot, and the bottom figure is the spectral reflectance. Here, x-axis is wavelength, and y-axis is surface reflectance. And the blue is MODIS, and orange is Landsat 9, and green is Sentinel-2, and red is Nmap. So I attended a hyperspectral workshop in Valencia this June, and I was quite surprised that hyperspectral satellite is very common. Yet lots of projects, lots of people are now using hyperspectral satellite, not drone, not tower-based, but from the space. And so, but that is the reality. One pixel just I chose, and you can see Nmap covers full shortwave from 400 through 2500. That is red color. That is full band reflectance. And then you can see there are all MODIS, Landsat, Sentinel. They are not completely aligned. There is some difference, but there are many reasons. First is landscape is heterogeneous. That is nature. And also spectral bands are different, and spectral resolutions are different. And most of all, the spatial resolution is different. For example, MODIS is 1 kilometer, Landsat 30 meter, Sentinel is 10 meter, and I think Nmap is, I forgot, but I guess it is more than 60 meter. And also temporal visit frequency is not identical. So some satellite overpass 11 or 1 p.m., so time is different. So I really think tower-based hyperspectral network is much, much needed. So my group has developed such a system because I think most people in the field, they measure BRF. But there are pros and cons. For example, in case of Dennis, he always measure albedo, hemispheric, to achieve the photon balance, and also it is much easier for the calibrations. And so then why not? So we try to combine these two together. So here we developed such a device. So first, we measure incoming irradiance, but in case of the outgoing, we measure both outgoing irradiance and also outgoing radiance. So here, orange color is, orange color, that is irradiance, and the red color is the radiance. So by using the prism. And we use the hyperspectral in the 400 through 900, and also the SIF, that is a 730 through 770. And also we added the SWIR. So there's multiple fiber optics, but only four optics. And that is reality. That is the case of the mixed forest in the Jeju Island in South Korea. And here, in the right figure, you can see there is a flux tower. And in case of the BRF observation, in case of the NADAR, the red circle is the footprint of the BRF observation. And in case of BHR, that is albedo, the hemispheric, it has much larger footprint. It is more comparable to the tower footprint. And so we measure both radiometric quantities. And you can see here, this time series, here x-axis wavelengths and y-axis is day of year. It is a spectral fingerprint. And this is BHR albedo, and that is the hemispherical conical reflectance factor. It is a sort of BRF. And here, this is the difference. So depending on the view geometry, the reflectance quantities are pretty different. Yeah, first, their footprint is different. Second, the angle is, how can I say, the angular characteristics are different. So to compare with the tower observations, I think the BHR is better. But if you're interested in calibrating or testing satellite BRF, then BRF is better. So there is pros and cons. So we try to measure both. So that is, okay, I think it is actually the drone image. So we installed all those hyperspectral systems in multiple flux towers in South Korea. Oops. So it includes the deciduous broadleaf forest and rice paddy and wetland and mixed forest and evergreen leaf forest.
very heterogeneous. And last AGU, I met one lady from the Christian Frankenberg group at the in the Caltech, and she told me that, hey, Youngryel, we installed LVUD sensor in the tower with $1,000. So wow, I was surprised, and I just checked, and we installed the same sensor, GNSS-based LVUD sensor, in our deciduous broadleaf forest site. So concept is very simple. It measures GPS signal the above tower and also below the canopy. So then apply the Beer's law. So then from that, we can quantify the VOD, the L-band VOD. Theoretically, it should capture the water content of the whole canopy, and also it is correlated with biomass. So it is the bottom right figure is the VOD of the hemisphere. So we just started to collect, and we are keeping collecting this data set. And also, I think this is also a recent paper. We really need a long-term spectral data set. In case of Flux Tower, think about harbor forest. Now we have more than 30 years. And many people are dedicated in calibration. In case of the spectral data set, I think we don't have such a long-term data set. So that has made many debates about, for example, global greening, browning, something like that. And that is recent paper in my group. And what you found that here is the red color is our updated data sets with the corrections in the across ABHR sensor calibrations, and also the orbital changes and modest ABHR, the normalization. And so our data shows that fairly persistent greening it is global scale. But in the past, the other data set shows very rapid increase before 2000, and after 2000, it is saturated. Actually, then make many big papers about recent saturations of the CO2 effect. For example, recent saturation of the water use efficiency, something like that. So I think we really need to revisit those big findings. But to do so, we need very, very well calibrated and long-term spectral data sets. And this is one photo from 2 weeks ago. There was a workshop in my university. All the attendants were shocked with this image. That is 20 years field-based fisheye image from the top of tower. It is in the Takayama. It is by the Canon Nishida Nasahara and Taiga. It is a pen records. You can see there is not so much difference in the greening, but there is a increase of the snow melting period. So with such long-term data set, we can interpret the spectral data set better. And that is overall my idea. So we need to integrate the low Earth orbit and also geostationary satellite. But most of all, in the Flux Tower, I think we need to augment the visible, thermal, and microwave, all the spectrums, and that keep continuing observations about the long-term records. Then we can track diurnal variations and isolating pixels within the footprint and so on. We can do many things. Okay, that's it. Thank you very much. Oh, actually, I'm hiring postdocs. So this is the last one.
Thank you very much. Okay, next speaker is our Stefan Metzger, something like that, from Atmofacts. He's going to present his work linking realms from ground to orbit, matching fluxes and states across scales.
Sounds good.
See if I can get this panel here out of the way. Looks good, I guess. All right. Thanks, Nicola, for the intro. Thanks for having me today. Super excited to be here together with you for those 2 days. My name is Stefan Metzger. Up until about a half year ago, I led the surface atmosphere science at NEON, the National Ecological Observatory Network that Dave talked about earlier. At that time, I set up my own science shop, AtmoFacts, motivated by the realization that techniques, flux spatialization techniques, might just be one of the ingredients that it takes to make eddy flux truly accessible and ready for real-world impacts. And so now we're going to explore some of that here. Linking realms from ground to orbit, matching fluxes and states across scales. So let's see if I can get that out of the way as well. Oh, this one probably. All righty. So the first thing that we may want to ask ourselves is, what are we scaling for? There can be all different kind of reasons. And what we're really trying to do here is to tie this workshop to societal relevance. And that can happen at these various different scales. For example, on the continental to global scale, we talk about net zero pledges that we want to scale into. At the regional scale, about public awareness and policymaking, and at local to regional scale, we talk about water, carbon, and pollution management. And so once we know the ends that we're working towards, that can then also inform the means that we're employing to get there. And there's various approaches. We highlighted 2 of them here. There's a straight shot approach where we're essentially saying, hey, what we learn at the micro scale, say at the site scale, that's directly applicable at grand scales. We can use those relationships directly. Or on the other hand, there's another approach, explicit nesting, where we say, hey, okay, we go step by step from local scales or regional scales to continental scales. They nest into each other, and they differ in some of the attributes in terms of transparency and simplicity that they're able to achieve. Now, to choose our means, we are going to explore in particular the explicit nesting a bit more. And so to choose our means, what I put together here is a feature set, how we can make direct atmospheric measurements like eddy covariance directly relevant for measurement reporting and verification. So what must our measurement actually be able to achieve in order to become relevant? And so you see those different rows. There's things in there, features like quantifies individual sources and sinks. We want to measure at least 95% of our emissions and not have a bias more than 5%, and so forth, and so forth. We can't be too expensive either, right? And so pitted against that is what you see is kind of the status quo to the far right here. What current techniques allow us to do, activity-based, in situ proxies, including soil coring, remote sensing and model proxies, atmospheric inversion. And they all have different characteristics in the sense of that feature set. Now, what can we as eddy flux and remote sensing community together contribute to that feature set? So there's classical eddy covariance, and when we look at that in terms of that feature set, it certainly addresses many of these points, but it also falls short in some of these areas that we're going to explore a bit further. So on the very top left here, that we believe something like a spatialized eddy covariance can actually help us get there, help us get the remaining 15 to 20% to truly make eddy flux relevant for the discussion of measurement reporting and verification and climate solutions. So let's explore those traits, those features a little bit, and how eddy flux might be able to get there. First of all, we want to be able to have less than 5% bias in what we are producing. And in order to achieve that, we need to account for quote unquote missing fluxes by satisfying the micrometrology. So essentially what we're doing at this point is we have like a large round peg, which is our eddy flux footprint, and we're trying to squeeze that into a square hole, which is either our control volume that Ankur talked about earlier this morning, that eddy flux needs to satisfy, so continuity of mass. It's either that control volume or it's a satellite pixel. And whenever you do that, there's going to be losses, there's going to be shavings. And so what we actually see is that with increasing heterogeneity, and that's a study that Paul did several years ago, that with increasing heterogeneity of the landscape, that this missing flux increases. Now, what can we do about it? How can we actually account for that missing flux? And so that's the idea where flux spatialization can actually help math to get from an observational puzzle to continuity of energy and mass. So you see on the left-hand side, this irregular shaped footprints or almost like plume envelopes. And they essentially equate to a leaky control volume. So we're not, by definition, not satisfying our micrometrology, our control volume here. And what about if we're able to actually stack those individual air parcels back to where they originated from, hence running the fluxes back on the wind, essentially, where they originated from. We stack them back where they came from, and then suddenly what we see here in this study by Kirschü is that energy balance closure is satisfied, even from a single tower. Now, the second point where spatialization might be able to help with is quantifying individual sources and sinks, and we've seen quite a bit about this today already, so I'm not going to belabor the point, but this is a slightly different perspective on the matter. So essentially, if you have two different emitters or sequesters, the time series get here is this mixed signal, right? You're not getting an activity, just temporal control signal, because you have more par at a certain point in time. If the wind shifts, you actually get a mixed signal because the wind is shifting and you're looking at different surfaces. So wouldn't it be wonderful if we were able to actually separate the controls, the spatial and temporal controls for these different surfaces and inform our upscaling with that? So we would gain a lot of statistical power by doing that. And so one way to go about this is to run high resolution fluxes backwards on the wind and ending up in a spatialization procedure. We do have 10 hertz, 20 hertz data points per second in our original eddy flux data. We already have them in the pocket. They're sitting somewhere in the database, but we don't typically readily use them. What we use so far traditionally are half-hourly average products, which then result in a somewhat obscure attribution to different surface areas. And that's brought us a long way already in terms of the relationships that we're able to discover over many decades. But we're also hitting a bit of a glass ceiling at this point when we really want to talk about attribution, maybe even in a carbon economy sense. And so that's where we believe spatialized eddy fluxes can actually help with that. And the idea is that these micro variations that our flux tower perceives and captures, that they can be utilized for time to space transcription of information into the spatial domain, which you see here on the right-hand side. And what you then get, like we've just been talking about geostationary satellites, for example, or remote sensing in general, you need ground truth. And so what you get with that is thousands of pixels of ground truth with sources separated instead every half hour instead of one half-hourly data point for mixed sources, which you see on the left-hand side. Last but not least, spatial acuity and representativeness. So we want to essentially be able, Youngryel, you talked about this just now, we want to be able to relate from our flux tower measurement to a larger region or maybe even to a continent. How can we get there? And so this is an animation of actual data where you see a classical flux tower. It's like a torch in the dark. Ankur showed a similar version of this presentation where we had land cover in the back. Here, the color of the torch that you see is your average flux. In this case, carbon flux. And you see it changes colors, but it also constantly changes where it's actually attributed to or coming from. When we are working with that spatialized eddy covariance, you're able to reveal the individual sources and sinks within the footprint by leveraging we talked about hyper resolution. So in this case, hypertemporal resolution information in the data, and are then able to marry that together with additional constraints such as remote sensing and so forth to get 10 to 100x statistical power out of our existing eddy flux station. Here's one real-world example. Ankur was showing that earlier as well, so I'm not going to belabor it. But this is essentially how, on the right-hand side, how attribution of carbon flux over farm can look like with such type of approach, and how it currently looks like with traditional approaches here on the left-hand side. So to close that out, we can essentially summarize that we can derive something like a right scaling recipe. So first of all, again, we want to ask ourselves, what is the demand of the task at hand? Is simple and fast what we need at this point, and then it's absolutely justified to go with a straight shot. And there's even ways, like we did earlier today from Jake Nelson and others, to then compensate for any potential biases and whatnot from the top down. So by marrying bottom up and top down approaches, for example. However, those don't necessarily work at the ownership scale. So, you know, they're still fairly large scale rectifications. The straight shot affords simplicity, but struggles with scale emergent properties such as continuity of energy and mass. So if we actually need that for individual MRV project, measurement, reporting, verification, and others, there's ways to get there through, for example, this explicit nesting and flux spatialization we talked about by means of propagating spatial and temporal controls separately, and thus making data more intuitive to use. So you can half-hourly map, which you can overlay over anything you want. You can overlay it over Google Maps. It's very intuitive. You immediately see where the flux is coming from, so to say, and serves as a flux tower multiplier. That's all I brought for you today, and I'm happy to talk more in any of the breakouts or after this session. Thank you.
Thank you, Stefan. Next speaker for today, last speaker for today is Kevin Tu from Qatari. His work titled Bridging the Gap Between Science and Social Benefit, Eddy Flux for Measurement, Reporting, and Verification of Grassland Carbon Sequestration.
Thank you for having me here today, and I hope to keep you all awake as the last talk. I used to work down the hill on UC Berkeley, so it's nice to have a reason to get past security finally and come up the hill. This one? All right. Okay. Let's try that again. There it is. You got it. Thanks. So my name is Kevin Tu, and I currently, as I mentioned before, I used to work at UC Berkeley. I spent 10 years in the big ag industry. I like to say watching corn grow using drones and satellites. And more recently shifted to the startup space, working in the nature-based solution space. And today I'm going to be talking a little bit about some of the work we're trying to do in bringing, bridging that gap between research, science, and sort of commercial applications for social benefit related to using eddy covariance or eddy flux for MRV or measurement, reporting, and verification, specifically in the grassland carbon space, and using eddy flux for constraining carbon sequestration estimates for that purpose. And want to start off with why focus on grasslands in particular as opposed to forests or other ecosystems, and just want to highlight in general that sustainable land management and conservation of terrestrial ecosystems in general is those are crucial for achieving sustainable development goals, notably which include climate change mitigation and reducing biodiversity loss, and also there are social benefits and community benefits to improving ecosystem function and the services that they provide, and carbon storage and sequestration being just one of those. But that's what we're focusing on primarily because there is a financing aspect to that right now in the voluntary market space or marketplace, where people are actually willing to pay for an improvement in ecosystem services through by way of carbon. And so what you see there on is a mock-up or cartoon of the different biomes across the land surface. And the work that we're doing is focusing on the temperate grasslands, which, as indicated in this cartoon, most of the carbon is that big green area below the land, below the soil surface. So most of the very little carbon is residing above ground in standing biomass. And the carbon pools that have importance in temperate grassland is really that soil carbon pool divided between organic carbon and inorganic carbon. But the dynamic pool that we're focusing on is the organic carbon. And grazing lands, just to highlight that, grazing lands, mostly comprised of grasslands, some savannas, occupy nearly half of the planet's land surface. And within the US alone, grazing lands cover about 20%, 28% of the land area. And about 20% of the world's soil organic carbon resides in grazing lands. And there is a large soil carbon debt, if you will, due to human activity, which has the potential to be restored. And that's kind of the carbon pool or that we're trying to restore. There is significant opportunity right now for nature-based solutions in grasslands as one of the world's largest ecosystems. In recent years, there's a massive increase in offset and insect credit purchasing, especially in nature-based markets. And grasslands are an underutilized carbon sink. And ranching specifically has historically lacked technology to scale regenerative methods. And governments, finally, governments around the world are dedicating a large amount of funds to spur more climate-friendly agriculture. So a little bit about background and context to Kateri. The company I work for is a startup in which Kateri provides end-to-end services focused on enabling landowners or being the handholders between the carbon buyers and the ranchers to really capitalize on the potential for nature-based solutions in grasslands. So we are a tech-enabled carbon developer, and as often it's, I think, convenient to think of a carbon developer as like a real estate broker or real estate agent, but we're simply a carbon broker instead of a real estate broker. So we're connecting the carbon buyers with the ranchers in this case, and we're doing the work that's needed to to provide the documentation for the project, make sure all the boxes are checked with the registries and the protocols that need to be checked, where we coordinate measurements in the field, including of which we're trying to expand to eddy covariance. And so one of the questions, of course, is where do flux towers fit into all this? And in general, there are many aspects when it comes to quantification of carbon in grasslands, in the soil specifically, anywhere from biogeochemical modeling to remote sensing, and the outcomes of management decisions that affect soil carbon. And also, there are aspects of data requirements that the registries need, the regulating bodies need in order to verify or validate that based on certain metrics, we're meeting their requirements. So EddyFlux enables these various aspects of our operations, and that's where we're trying to go with EddyFlux. Within the research arena space for rangeland carbon sequestration, EddyFlux has emerged as the de facto method. And that's largely because there's a lack of carbon stock measurement change over time to really quantify that carbon sequestration based on soil carbon measurements. There's a lack of that kind of data in rangelands that in order to make some meaningful constraint to models, these research efforts have resorted to using eddy covariance and EddyFlux data, such as provided through Ameriflux and Neon, because they provide a rich data source that can help constrain these type of ecosystem biogeochemical models. And namely, most notably, recently there's a rangeland carbon tracking and management system, which is leveraged 61 Ameriflux and Neon tower flux data sets to develop and test their model. And secondly, there's been a large effort recently. There's a project called 3M, or Metrics Management and Monitoring, which is a project that's been funded to the tune of about $19 million, and to better understand how ranged land management can impact ecosystem function and carbon sequestration in general. And within this system, they have deployed 30 new low-cost towers. So alternative to the conventional eddy covariance, but they've chosen to go the cost of the low-cost flux towers, and they've deployed 30 of these. And it should be fairly obvious that in order to do that at that scale of 30 new towers, you would have to, it would be millions of dollars just to finance or to pay for the cost, or to cover the cost of a conventional eddy covariance system for those number of towers. And you can see in the image there are these low-cost towers, and you can see 3 of them within a small space, because at these 3 core sites they have in different ecoregions, they have about 10 of these low-cost towers deployed within a small area in order to monitor the different management impacts within that within the small area. To be able to do that with conventional towers would be, of course, much more expensive. And so this study, the 3M study, has deployed currently 30 of these low-cost towers, with plans to probably roughly double that. And to note that they are doing this in combination with other measurements like SOC stock measurements, so standard soil sampling combined with element dry combustion, also combining with remote sensing and ecosystem modeling. Within what we are embarking at Kateri, we are doing a pilot study to evaluate the implementation of these kind of low-cost eddy flux systems for project development. So trying to translate that research, which I just mentioned, into action, into actual land management improvement. And what we're working on right now is deploying 4 of these low-cost eddy flux systems in 4 of our project areas that range in site conditions in climate, soil, and vegetation. And part of the impetus for going down the path of using these low-cost systems is obviously because they're scalable, because of the cost, but also because based on the knowledge that prior studies going into this have established that when they are deployed in a proper manner, these low-cost systems can be viable alternatives to conventional eddy covariance systems. And the plan is to use this data for calibration and validation of rangeland carbon flux models. These are ecosystem biogeochemistry models in combination with typical soil organic carbon stock measurements. So the 2 combined will hopefully provide that constraint to robustly develop and validate reliable models. And I will mention that there are additional low-cost systems in development that we're keeping an eye on, such as the Lycor is developing a low-cost eddy covariance system analogous to their low-cost ET system. There are alternative flux methods besides eddy covariance that might provide comparable and data for these kind of purposes, such as the variance Bowen ratio method or Bowen ratio method and surface renewal. So there are other methods that could be used with flux measurements that could be used in addition to eddy covariance to provide low-cost information. And just want to highlight some of the challenges that we faced in trying to bring eddy covariance or eddy flux measurements to implement as part of the graphs these type of NBS projects that we're trying to develop. And one is the cost. Obviously, as I mentioned, the cost of conventional eddy covariance systems is prohibitive to use them in these types of projects. And so low-cost systems are really the viable alternative. There's also so we have to overcome that cost challenge. Another challenge is that rangelands typically occur in what is generally non-arable land, and which is generally land which also not only is typically dry lands, but also just landscapes that have more topographic variation than you would have for a flat area that you could do row crops. And because of that topographic variation, it's a bit more challenging for the placement of towers to satisfy the requirements you need for eddy covariance. Another challenge is the accuracy of not only conventional systems, but also the low-cost systems. So we're still addressing how to ensure that we are getting defensible cumulative NEE or net ecosystem exchange measurements to be able to satisfy the requirements that are necessary for accrediting and by the regulating bodies like the registries. So we're really trying to address how do we minimize uncertainty and how do we ensure that we are getting accurate and precise measurements. And another challenge is that with these kind of type of projects that we're doing is that they typically, again, rangelands typically are in dry land systems, low productivity systems, which because of their low fluxes, they generally are going to be near the detection limit of conventional eddy covariance. And so that's really putting these low-cost systems to the test when it comes to being able to resolve changes from year to year in, say, an annual CO2 budget. And finally, another challenge in terms of implementing eddy covariance with these kind of projects is that the regulating bodies like the registries that develop the standards and the protocols that we have to adhere to don't currently permit the use of eddy covariance for CO2 or using the eddy covariance to calibrate, validate models. Although that, as we've heard today, some of that that situation should change, particularly if we, as a community, put in place guidelines and protocols that can facilitate the incorporation of eddy covariance in a wider extent and advise as a community the proper use of eddy covariance to agencies like the carbon registries. To give you an idea of the next steps where we're going with this approach, the idea is to have sort of a system of systems method where we're combining eddy flux. We're not just relying on eddy flux, or we're not relying solely on soil sampling and soil organic carbon stock measurements, but combining the two, also combining it with real-time animal tracking, so we know where the animals are at all times. It's so where we can have a better understanding of their impacts, and combining with remote sensing inputs and integrating everything with models. And so combining everything together, we can have a better constraint on and have more reliable estimates of what the ecosystems are doing both in terms of carbon, but also in terms of water. And also the idea is to move away from what is currently would be called a measure model approach, where you measure initially and then you use a model to forecast or in the future through the project years, you use a model to quantify soil organic carbon. Instead, we'd like to be able to rely on actual measurements. And so eddy covariance or eddy flux in general would provide a way to move towards a measure approach. And part of that would be being able to implement flux towers in a fashion more similar to an experimental design, where you have towers located in control locations that represent either conventionally grazed systems or ungrazed pastures that could serve as a baseline or reference for throughout the project period. And finally, building on the last talk, that we'd like to incorporate the technology and the techniques and methods that Stefan just mentioned related to flux mapping, where we can have, it would be even more cost effective and efficacious if we could have a single tower monitoring different pastures simultaneously. And that way you could then combine the live animal tracking with the real-time flux measurements to then know the impact, to really quantify the impact of the animals on the fluxes. And you can see here in this picture some of the collars that the animals have on them. These are used for not only tracking through GPS positioning, but also through virtual fencing. So instead of actually the rancher, it enables the rancher to, instead of using actual fencing and going out and having to move that fence to move the livestock, they can actually, or they just draw boundaries in a online interface, and then the collars can be used to constrain or move the cattle around to different areas of the ranch. So that concludes what I have for you today. So thank you very much.
All right, everyone. I would like to invite the speakers here so we can ask some questions. Any question from the audience?
I have a question for the grazing projects. Is it part of your setup? Oh, you hear me? Is it part of your setup, or is it part of your evaluation to see if you can move the towers for them, like the low-cost towers, to also be mobile, so you could cover more land with them? Like, how important is it to measure the whole year?
Ideally, you would measure in one spot over the course of the year, so you can really get that annual budget. But of course, it might be more cost effective to move it around. Maybe you could use a mobile tower to provide the data to create a machine learning model or something like that, or to validate the model within a given location, and then move it to another pasture or another location. That might differ in soil conditions or management conditions, but unfortunately, the tower, even the low-cost systems that we're working with, the vendor that provides those, it's not really feasible to. They're not really set up, operationally, logistically, to do that. But it certainly could be done, but just a logistic challenge.
See how uncertain that would be.
Sorry, I couldn't quite hear.
You could still calculate the uncertainty of if that would be worthwhile in the future with the setup you have, because you have so many towers.
Yep, that would be, yeah, it'd be nice to run through the numbers on that to work that out.
Kevin, are you planning to publish those data sets in Ameriflex?
So technically the ranch, so we get into legal issues of who owns the data, and the ranchers, I think, technically own the data, although we might own it. So it's a little bit of proprietary issues we have to deal with. But even like the 3M project I mentioned, that's I think those are going to be available. Yeah. And I should mention that the vendor for that is probably one of the largest networks. That's maybe second to Neon or bigger than Neon. I don't know.
Just a comment on that one. As far as I understand the licensing agreement, Quantera claims that they own the data, so you actually don't own the data, and they're not giving you the raw data anyway, so you can't really verify if whatever they're calculating and putting out is actually correct. So it's a bit of a it's really problematic actually, and And just to add on to that one, if you followed the literature out of New Zealand, there's a massive problem looking at pastures and only looking at the CO2 sequestration. Again, the same problem of not really having methane in particular and nitrous oxide, especially if you have animals on the whole pasture. That is just it's a huge systematic problem.
Yeah, of course, we'd like to move towards flux systems for nitrous oxide and methane as well. It's just another level of cost hurdle that we have to get over. Yeah, I can't remember the first question you had, but oh, the ownership. Yeah, we do provide, or the Quantera does provide obviously the flux data. They don't provide the raw data, but they provide the fluxes. So, and I think that's what maybe might be of use to the community in general. Although the raw fluxes are, of course, well, we're free to use the product, the flux data, not the raw data. Yeah, and then also I think there's another good point is when it gets to actually using that type of data for registries, I think there really does need to be that transparency to be able to, how do you verify the data if you can't have access to the raw data, you can't go back and check. So we totally agree. And that's something we're trying to push them on.
We have some questions from the chat. So questions to Stefan. Could you elaborate on how the specialized EC estimates are made? Could you elaborate on how the specialized EC estimates are made? At the covariance estimates, yeah, specialized ones are made.
Thank you. Great question. Thank you. So the main difference is we already use footprint models. We've seen a lot about footprints today. Oftentimes they are made on a half-hourly or sometimes even daily or monthly basis footprint climatologies. So the main difference with the flux spatialization is that we do this every second or every minute, which allows us to discern a lot more how flux covaries both with the surface that it's sampling and with any other temporal drivers such as radiation, temperature, and so forth. And so that essentially creates an inverse problem with the flux footprint matrix that you're able to resolve in the most basic sense. And as part of that solution, it's also possible to introduce additional data layers, such as remote sensing, if you know something about your soil and so forth, that can help sharpen the picture. So that's to get an intuitive sense. And I'm happy to talk more about technical details. Thank you.
Sorry, question for Youngryel. So on one of the slides, you mentioned that the GeoSIF is higher in the morning. On another slide, the results show GPP is higher in the afternoon. Any thought on that seeming contrasting dynamic variability?
Yeah, actually, the Lee et al. 2023 showed higher GPP in the morning. So I think, yeah, Wheeler, yeah, misinterpret the figure.
Okay, question from here.
Yeah, thank you. I think it's very similar to what Denise is asking. It's for Stefan. It says, but aren't the sampling errors large with short time steps? And my question is about the same thing. It's like when you are calculating fluxes using the covariant technique, you are using it like at least for 30 minutes or at least 15 minutes so that the area that you're measuring is able to carry all the concentration, right, to calculate the fluxes. Is using the high frequency data different in a way how you calculate fluxes?
Yeah, great question. We've been struggling with that for a long time. Yes, it is different in the sense that we do not use a standard block average, which you would then have to reduce your 18,000 samples, let's say, in half an hour down to 180 or whatever, like, really small. And with that, I think what you're alluding to, what you lose is oftentimes these contributions by larger eddies in the atmosphere that take a while to go past your tower. And so instead of using a block average and just doing that more often, we use time frequency decomposition. So essentially, when you think of MP3, then the song is being decomposed in the different wavelengths at different times, which allows you to also at very small time steps, like as you're listening to the music, or here in this case, as we're tracking the flux, to include all the different frequencies, say, that we're listening to or that contribute to the flux. So that's how we get the full inclusion and this, and are not suffering from systematic biases.
My question is about Kevin and Stefan, and just curious, switching gears here completely, but your perspective from industry, given that we have a lot of students and postdocs, academics, faculty perhaps who are thinking about what life must be on the other side. How is it? How's life? What do you enjoy about working as a scientist in industry, and what do you find frustrating or more difficult? And ultimately, would you advise it?
Somebody's So I'm still very fresh in that, and I can certainly say it's scary. It's but at the same time, what I get out of it is a lot of flexibility. I am very passionate, as we talked about earlier, about making some of these tools more broadly accessible and usable, and hopefully through that the transparency of eddy coherence is more accessible, and working across both actually industry and academia and being right that interface facilitates a lot more flexibility, I feel, in being able to, and also building bridges. So we talked about carbon earlier this morning in one of the slides. So to really make our scientific expertise and insights matter, and creating that conveyor belt between the sciences, as many of us are sitting here together, and bringing that to real world and industry applications. So that's certainly for me the most fascinating part.
I will interject there that within industry, it's need to recognize that there's a not so scary side of industry where you get paid a lot in big ag, and the startup side of industry where it's a little less. There's more risk. Yeah, I think and I will add also that I think it's extremely rewarding to work in to be able to apply science and research in general in an applied fashion, and so particularly when you can do it with something that you're passionate about. So I think that is an extremely rewarding aspect if you can get that, if you can strike that balance.
So another question from the chat. So question to Youngryel. She said, if we are even able to estimate hourly fluxes from remote sensing, well, yeah. So given that we can estimate hourly fluxes from remote sensing, could you share a bit your opinion on what might be the current challenges for improving flux remote sensing methods?
The question is the challenge in estimating hourly fluxes from remote sensing?
Yeah. Your opinion, yeah. Current challenges for improving flux remote sensing method.
Okay, I think first, we need computer resources, because hourly means that there are lots of data sources. And unfortunately, NASA and NOAA, they don't provide the BRDF product. So one have to download and process everything. So actually, it's never trivial. And in terms of mechanism, I think still Yeah, so what I showed is, and I repeat, it's just structural changes of, so it does not include physiological variations. And in case of the SIF, of course, it can include some physiological information on the diurnal scale, but I think still the level of depth in mechanism understanding on the diurnal scale is still very, very incomplete. So I think still we have to look very deeper into the physiological knowledge on that aspect. I think it's still, yeah, we need more work.
Okay. Hi, as the day has progressed a little bit, I think I'll ask a more philosophical question. So, or provocative, let's see. And so my question is, you've all been talking about upscaling, but essentially what you've been doing is extrapolating the data. And so my question is like, what is really the upscaling part? So how does the mechanism change, or what emergent patterns do you actually get by just going from one scale to another, from like your point source to the more regional or global scale?
Is your question aimed more at the scientific usefulness of that type of exercise, or is it aimed more at what do we as humankind get out of that?
I mean, like just from like the scientific point, I mean, what you've been doing is you essentially go from like an information you have at one point and extrapolate it to a wider area, like a spatial scale.
Mm-hmm.
But the thing is that if you're talking about upscaling, what you can have is that actually going from one scale to another, you can have emergent behaviors, right. You can have different patterns, and this is something you can also have in the temporal like dimensions. So my question is, okay, are we going beyond just extrapolating? Are we actually going towards upscaling of the data and information we're having?
Yeah, that's a great comment. And you might recall from one of the figures that I was showing earlier that this was this nesting figure where we can do exactly what you just described. We can take the straight shot and just say, hey, what I observe here on my side, that ought to be valid across all wetlands in North America, let's say. Yeah, and then we're probably cutting it short if we're extrapolating in such a way. And if questions become complex to such an extent, what we can then do is creating these matching layers to actually facilitate the emergence of scale-related behaviors between the interfaces. And that's where some of the techniques that we were talking about earlier, I've been talking about flux spatialization, for example, can actually, what we see, help with that. For example, creating that mass continuum, because now you're actually able to map your control volume. So you can actually count that out and suddenly you satisfy certain methodological assumptions and things begin falling in place with regard to scale emergent behaviors, for example. And I believe quite a few of the techniques can actually be used in both directions, upscaling and downscaling. So eddy covariance is not the smallest scale that many of us work at. So oftentimes you have soil plots or plant samples or individual trees that you want to relate to. And if you can break down, Youngryel, you talked earlier about, I think, 3-meter resolution, for example. If we can do this in a credible way that accommodates scale emergent behaviors, then we can actually zoom into the object of interest as well and create relationships there that help us cross these scale boundaries. Does anybody want to add?
So my question's for Kevin. Just curious, you mentioned that a lot of the carbon storage in these grassland sites is in the soil, and I know soil types can vary at very small spatial scales. Are you using soil maps to inform some of the modeling you were talking about doing, or I guess how are you dealing with that variability?
Well, I can start, with the protocols that are in place that we have to adhere to for the crediting. The method that they that we have to, or the requirements that we have to meet are generally, are typically met by way of randomized, stratified randomized sampling, where the hope is that, and generally that works out in the real world to be maybe one core sample every 20 acres or more. And the idea is that in theory, that by taking that over, the project area, and you have to stratify according to soil type and the factors that are believed to drive soil carbon formation, like soil type, maybe mineralogy, texture, the climate or weather variables, maybe precip varies across the landscape, and then vegetation conditions, that kind of thing. So factors that drive that variation in soil carbon formation. As if you sample according to how those fall out, and you have samples representative of that variation, and hopefully, and you sample in a way without bias, then hopefully you will end up with a representative result that captures that variation. But that's why I think a system of systems approach where you tackle the problem from different spatial and temporal scales provides a better constraint than just relying on that kind of soil sampling alone.
There's a question here.
Just commenting or asking more on that one. You're using the words of hope and so forth, and I'm a little bit worried about, have you actually done soil sampling on those fields, and what is the standard deviation that you found in there, and have you done soil sampling in close quarters, such as multiple soil samples in a, say, a 2x2 square, and what is your standard deviation across that one, and what does that, if you have done that, what does that lead you to understand about spatial heterogeneity?
We have not done that kind of high density spatial sampling. Others have done it within crop fields, so it hasn't been done in rangelands, so that needs to be done. And yes, we have actually done as part of every project that we developed, there are baseline samples so we go out and measure. We hire companies that go out and measure and do the sampling design that we then approve, and they go out and sample. So we have done that sampling. So far in the ranches that we've worked with, probably half a dozen that we have results back so far with the initial baseline sampling. I believe we're looking at, I'm trying to remember numbers off the top of my head. It's definitely within that 5% variation that we're trying to target at 95% confidence. So we're meeting, so to date, the sampling that has been done suggests that it is sufficient to detect change over time. For example, when we come back and measure again, we should be able to detect the change that we're hoping to. But of course, it's something we're continually looking into and trying to monitor to make sure. There are ranches that are more heterogeneous that have not come back with those kind of favorable numbers, and the costs skyrocket because the number of samples required to decrease the uncertainty to levels where we can actually hope to detect change over time. The costs just can get out of control.
This question is also for Kevin. When you're talking about the soil sampling and the SOC socks, are you just talking about kind of bulk SOC, or are you also looking at kind of the different potential fractions like mineral associated, so organic carbon, et cetera, to kind of compare with the flux measurements that you're getting?
Yeah, just to a little background there. The notion is that the different fractions might have a different permanence to them, right? So the maybe a mineral associated so organic carbon might reside longer and be more resistant to degradation over time, as opposed to the maybe particulate organic matter. We are not currently measuring those different fractions, but it's something that we want to do. So we're trying to build that into the economics of the business to be able to incorporate that additional cost to provide that additional information. But it's something that we understand is important to do, and there are not all the labs are set up to do it, and so it's that's another challenge.
Short question for Kevin. What is that makes low cost? What is the name? Quantera systems. Why are those low cost? Is that a technology or
the Quantera systems, the low cost systems that I mentioned, they are low cost by way of the fact that they are, you could say, saving money on the CO2 sensor. They use a fairly conventional sonic anemometer, but the CO2 sensor is a slower response sensor. Slower response also for humidity measurement. Anything else?
All right, thank you, everybody. I think we should try to go at the breakout session. The last one is being very intense day, but we have the last half hour. And so let's give an applause to the speakers and let's divide in group as before.